Greetings. This lecture will be on flow and velocity measurement, kind of part two to our last lecture, which was on measuring flow. Here's a review of what we covered in that. So we started with mechanics, fluid mechanics review. We covered Reynolds number, viscosity, laminar flow, and turbulent flow. Then we started to get into the flow measurement. We talked about units, we talked about applications, and then we got into the pressure differential devices. So the premise of these was that the flow area reduction yields a measurable pressure drop. Bernoulli's law and Reynolds number give us relation to velocity, so you get the velocity from measuring that pressure drop. And the conservation of mass relates velocities at the two axial locations, and all this combines to yield the flow rate. We could get that in a mass flow rate or a volumetric flow rate. The head meters, or these pressure differential devices that we covered, were the Venturi tube, the flow nozzle, and the orifice meter. And we made pretty big points about the energy losses these produce, and just mention that they can measure compressible gases. We just need to include that expansion factor y in the equations to account for that. There is an equation for that as well. So here we have a question that is a review from that lecture. So it says, when using obstruction flow meters with liquids, which statement is true? Pause it, think about it, welcome back. So when using obstruction flow meters with liquids, which statement is true? A, can only be used when flow is considered laminar. B, velocity or dynamic pressure measurement is required. C, flow calculations based on incompressible flow are utilized. Or D, the flow meters are designed to be symmetrical so that eddy current losses cancel out. There's a key word in the question that you might kind of fly past that helps you decide which answer is the right answer here, and that is liquids. So because it's liquids, then it's incompressible flow, and none of these others are true. So it's that one. I want to mention this. It's just, maybe this is a little bit of trivia, but the practice of using an obstruction to measure flow has been around for a very long time. Here are some stones that were put in the Nile. Ancient Egypt used this to measure the flow of the Nile. This meter here obviously isn't ancient Egyptian, it's modern day, but that stone is what they used from way back when. And if you go back even further, back to the cradle of civilization in Mesopotamia, there's, I'm not going to pronounce the name of this, it's like the Jarawan Aqueduct or something like that, but they believe now that this aqueduct is what brought water to the hanging gardens of Babylon, which is one of the wonders of the ancient world. They always thought that the hanging gardens of Babylon were in Babylon, as in the city, but Babylon was an empire, and it seems from some recent findings that the hanging gardens were actually in, I think, this is Mosul, or maybe it's Mosul, or Tikrit, I think it's Mosul, but in Iraq, and it was the ancient city of Nineveh, so one of the other main cities of the Babylonian Empire, which is now modern city in Iraq. But they, through using, I think it was that they used LiDAR, and they ended up finding, well, they used some references in some cuneiform tablets that they found, something like that, that allowed them to figure out that the hanging gardens of Babylon were actually in Nineveh. And then, it's a war zone there. At the time, they weren't able to send people in, but They used LiDAR, they located it, they got some locals to go in. All of this is covered in this documentary. If you're interested in that kind of a thing, I thought this was a really interesting video or documentary. I like history and I like engineering, obviously. So this is a really good combination of that. One, they talk about measuring the flow, and they would divert flow to the gardens depending on those measurements. And then once it got there, also another interesting thing they covered was how they used the Archimedes screw to get the water up to the top of the gardens, and that the Archimedes screw or pump, that was thought to be Archimedes or ancient Greek, which is thousands of years later, and it was a somewhat shocking discovery to see that ancient Babylonians were using these to pump water to the top, far before the ancient Greeks were. Anyways, I digress. Let's get back into this. So we're going to move on to a different type of flow meter. This first one is the thermal mass flow meter. So the premise of this is you have a gas flowing in a capillary. So here's the capillary. So you have the main flow in this sensing tube capillary. It's under constant heat flux. Let's say this again. I'll read it like it says here. Gas flowing in a capillary under constant heat flux is utilized to measure mass flow rate. So remember, heat flux, that's the rate of heat energy transfer through a surface. So a constant amount of heat is applied. And then if it's moving faster, it's not going to heat up as much. So you're not going to get as much of a temperature difference between T1 and T2. If it's flowing more slowly, then it will heat up more between here and there. We're going to get to an equation, but let's read. A lot of this might say what I just said, but let's read through it. It's good for reinforcement. So we want to use for laminar flow. So this won't work for turbulent flow. If you need to measure turbulent flow, look at one of the head meters that we just discussed. It can be used for either gas or liquids, though. So like I said, you add a defined constant amount of heat, and then you measure T1 and T2, and from that you can calculate the flow rate. So lots of different stuff on this slide. Let's start here. So the meter is designed so that the ratio of the sensing capillary flow and the main flow is independent of flow rate. So it doesn't mean that, so what this means is that if you speed it up, you're not going to have more or less flowing here than you would if you hadn't sped it up. So it can be used for multiple different flow rates as long as you stay down where it's laminar. So that's what this bullet point says here. Flow must be laminar, so low flow rates. And compressibility is typically not problematic. So like we said, you can use it for a liquid or a gas. Now let's get to that equation. So Q, the heat transfer rate, equals the mass flow rate times the specific heat. And we have an example of the units here. I'm going to show an example of this here very soon. Then we have T1 and T2. And T1 and T2, so say if you use your specific heat, it doesn't really matter if it's in degrees Celsius or Kelvin, because it's a change, right? The magnitude of that change is going to be the same whether it's Celsius or Kelvin. So you just don't use Fahrenheit or Rankine or something like that. So most often this is arranged like this because you want to determine the mass flow rate. So you need to know how much heat is being transferred to that capillary. You need to measure the two temperatures, and then you should just know the specific heat, which is essentially a constant for this. It shouldn't change strongly with temperature. You do that, you can get the mass flow rate. And then with the other flow meters, or like with the other flow meters, we divide that mass flow rate by the density of the fluid that's being measured. We can get the volumetric flow rate, Q. Sorry, I had to check something there real quick. Let's move on to that example. I just wanted to make sure I was actually recording the audio. I started another video last week and I got a decent way into it before I realized that I was on mute. But we're all good, so let's continue to charge forward. This online delivery has been challenging for all of us, but we're almost at the end. It's last week. We'll make it through it. Here's the example. 150 watts of heat is applied to a capillary tube. Calculate the flow rates. We want the mass flow rate and the volumetric. So we're given the specific heat, we're given the two temperatures, and we're given the density. So we just need to use that equation that we were given here. You see that transferred here. We just start plugging things in. So this is fairly straightforward, right? For this, we're just plugging all these in. All these units work out nicely. We end up getting the joules canceling out, the degrees Celsius canceling out, and we end up just getting a kilograms per second of 0.0298. But the only tricky thing would be maybe if this was in Kelvin or something like that, just to, maybe there might be kilojoules or grams or something. You might need to do some unit conversions, but it's kind of hard to go wrong with this equation. Then the conversion to the volumetric flow rate is just this one from last lecture. I think we showed it on this slide too. So you just divide that mass flow rate by the density, and I think we were given that. Here it is. So that's the density of that fluid. So from that, you can get the volumetric flow rate, meters cubed per second. That one's very straightforward. Okay, here's another question for you. Pause it, think about it. Assume you're back. So thermal mass flow meters. Of course you're back, or you never left. Anyways, let's get into the question. Thermal mass flow meters rely on the requirement that A, flow through the sensing tube is laminar, B, flow through the main tube is laminar, C, flow through the main and sensing tube is turbulent, or D, flow through the main and sensing tube is laminar. Of course, since you already paused this and thought about it, you're all geniuses, so you know the answer is D. Remember, we said it needs to be laminar. The next flow meter is the variable area flow meter. So here we have some illustrations of this. The premise is that the flow area of the meter varies with flow rate. So we have, where's my cursor? There it is. We have this around this float in here, we have an area where the fluid is going to flow. And depending on the height of this, then that area is going to vary. That's the gist of what we're going to get to in the calculations. You also can just see that it's tapered, so the area changes in that way as well. But primarily, we're going to be interested in this annular area. It's the ring around the float. The flow rate is determined by sensing the position of the component causing the area change. It can be used for both liquids and gases. Well, this here, we kind of blew past this, but we'll cover it more in the next slides. It'll make more sense as we dig into the equations and all the different forces acting on it. So here's a real flow meter, and we see a section of it to see what's happening inside, and we see that float. This is the main area there. But so one thing, note, these are always vertical. These need gravity to work. There's going to be a different type that we're going to look at that can be used horizontally. another variant of this is the rotometer. So this one, you blow into it to assess lung function, and it'll go and it'll stop at the peak. So it's a peak flow meter. And this is used to assess lung function, like I said, in pre-surgery or people that have asthma, chronic obstructive pulmonary disease, COPD. The equations that we're going to need. So we start with a force balance. So here are those tapered walls. We have the flow going past. We have our float. Now the three forces that are going to act on this, we're going to have a buoyancy force, we're going to have a drag force, and these are both going to be acting up. And then we're going to have a weight, which acts down. Then I said that ring around the float is the annular area. The annular velocity is the velocity of the fluid through that annular ring, where that's going to be a pretty key thing that we want to get to. It won't be our final thing that we want, but that's what we're trying to get to. And the volume of all this is important too. So if we just create this force balance equation, the weight equals the buoyant force plus the drag force. So we need to get equations for what each of those are. So the buoyant force, we have the volume of the float times the density of the fluid times gravity. Remember, a buoyant force is just the weight of the displaced fluid. And then the weight is going to be very similar to that, but this is the weight of the float. So we just change out the density of the fluid that was displaced with the density of the float. And the drag force is the more common one. So we have the drag coefficient, we have the frontal area of the float, we have the density of the fluid, here we have the annular velocity squared, and we divide all that by 2. Now if we take these three equations and combine them using this, we get this. And so all of that I walked through, but we have it again over here. The only thing, I don't know, I said gravity, and you know G's gravity. So we have this equation, we just need to rearrange it for the annular velocity. Here we go, that's that. And then, like I said, the annular velocity isn't going to be the final thing that we're after. We're going to want to know more in terms of volumetric flow rate. So the volumetric flow rate is going to be the annular velocity times the annular area. And then something else, so that would be if we're measuring a liquid. If we're measuring a gas, then the density of the float is much greater than the density of the fluid, of the gas. So in that case, we can get rid of this term, simplify it down to just that. So all these equations are what we walked through. Now a little bit of information getting to how this is made practical for somebody using it. The first thing is the drag coefficient is approximately independent of the float position. So no matter where this is vertically, drag coefficient is the same. That means that annular velocity is going to be nearly constant. Since our volumetric this means that therefore our volumetric flow rate is proportional to the annular area. So as this pushes up and the annular area increases, it means that the volumetric flow rate increased. And then also these are designed so that the annular area is a linear function of the vertical float position. So the vertical float position is a linear function of flow rate. So the float itself, wherever that is vertically, that indicates the flow rate. There are a couple different versions of this. You might have the scale just reading as a percent of the full scale. And in that case, then you're going to need to use tables or other data to find out what the actual flow rate is. But if you were say it was only meant for measuring water, then you could have the scale directly in the units. So the reading depends on the flowing fluid properties such as pressure, temperature, etc. The tables, the correlations you get from the manufacturer account for that. This isn't a very accurate device, though. 2 to 10% of full scale, the error you might get. Like I said, typically must be used vertically. Another complication is that it doesn't work very well for highly viscous fluids. High viscosity fluids stick to the float. That's this pink goopy stuff here is that viscous fluid sticking to the float. That increases the frontal area of the float and increases the reading, increases the drag force, right? This is the horizontal one. Essentially, it's the same, but instead of gravity, you have a spring. Spring-loaded tapered plunger. The plunger is deflected by flow through an orifice. The displacement can be related to the flow rate. Can be used horizontally. Okay, which statement best describes the error induced by a high viscosity fluid in a variable area flow meter? Again, pause, come back. So the answers are high viscosity fluid sticks to the float, increases its area, and increases the reading. B, the pressure is too high, resulting in readings higher than actual. C, the higher viscosity fluid plugs up the flow meter. Or D, the high viscosity prevents the float from rising as it should. So remember we said this, we said A. A is the correct answer in this case. Next, we have the vortex shedding flow meter. So this one, we have a prism or cylinder. It's inserted into the flow, and what it does is it creates these alternating vortices. And you have a sensor that's going to measure, or not so much measure, but it's going to count. So every time one of these vortices pass by, there's going to be a count, a signal, and it's going to keep track of those. And however many of those there are in time, that's going to let us know how the flow rate. The equation for this, so this slide first just says the procedure for that. You place the cylinder in the flow field, you measure the frequency of the vortices, and then you calculate the flow rate. Now the equation for this, the linear velocity v is going to be the vortex frequency. So however many of those pulses are counted in a second. And then you have the cylinder diameter. Then you have the Strohal number, which is typically roughly 0.2 to 0.21 if you have a Reynolds number from 500 to 100,000. So you could just use, say, the middle of that for a lot of fluids. So remember, this is dimensionless. This is going to be in, say it is in however many pulses per second. Maybe you could do it in, if it's really slow, maybe you want to do it per minute or something like that. But usually when you have an F like this, at least in acoustics, it's hertz, so it's in a second. But if it's slower than that, it could be per minute. And then when you have the cylinder diameter, whatever the dimension of that, you're going to have that dimension over the time dimension. This is dimensionless. So that's going to give you a velocity in terms of length traveled per time. And if you want to get the volumetric flow rate, you just multiply that velocity times the area of the cross-sectional area of whatever that flow is moving through. So here we have a turbine flow meter. These could be measured to, these can be used to measure wind velocity or river flows. Basically, the flow is going to rotate this, and then a magnetic coil pickup is going to pick up the pulses. So much like the concept of counting the pulses, relating that to what the flow is. Here we're counting the pulses. I'm not so sure that this semester we got to get into the magnetic pickup coils a whole lot, but if you have, so say you take a magnet and you wrap it, you have a coil wrapped around it. That creates a magnetic field. And then the magnetic field creates, the magnet creates the magnetic field. You have the coil wrapped around it. And if something metal moves through that magnetic field, it distorts that magnetic field. And that magnetic field distortion ends up resulting in a current produced in the wire. Since that current, or since the wire wraps around it a bunch of times, that change in the magnetic field that induces that small current, it induces it basically in every coil, and they all sum up together to be a signal. It's much the way that some of like the less expensive microphones work, or if you play electric guitar, it's how the electric string vibrating over the pickup. It's that same concept. You're just creating a signal that you can then, you're transducing that mechanical motion into an electrical signal. And that's essentially what's happening here. That turbine is rotating from the flow. There's going to be a magnetic pickup coil on there. So every time one of those metal blades passes by, there's going to be a signal, a pulse that pickup picks up, and then it uses that to determine the flow rate. So this is a much more accurate device. This over here is an anemometer. So this, mechanical engineers that get into building systems design, so that they're designing mechanical systems for buildings, which is a huge category of jobs for mechanical engineers. I think 25% of mechanical engineers go into that job according to the Labor Bureau statistics, or I said that wrong, the Bureau of Labor Statistics. I think that last one is the right one. I don't know why I said the first time, but that it's a big job category, and those jobs are all over the place. It's not like you need to be in a center of industry for that type of a job. But generally what a mechanical engineer doing that job will use this for is to, once their design has been built, they'll go around and use this as part of the test and balancing. So just making sure that all the right airflows are coming out of the diffusers of their system. Maybe all the dampers have to be adjusted to balance the system if they're not getting what they designed. It's one common application of this for mechanical engineers. So this one is an electromagnetic flow meter. Here, so we have you have some pipe, you have a fluid flowing through it. There's a magnetic field that's generated, and so in this case, the fluid needs to be partially conductive. If you have deionized water, it's not conductive, so that wouldn't work. But so long as the fluid that's flowing through is conductive, it can measure the flow. And a big advantage of this too is that there's nothing that's just, there's no in-stream anything. There's no obstruction. There's no loading error from this. That voltage is just induced by it's induced into the electrically conducting fluid, and it's measured on the other side. And the strength of that helps or is related to the flow of the fluid. So you can use it in slurries and corrosive or abrasive liquids. There's no energy losses. There are a lot of big advantages to this type of a device. Here we have a positive displacement flow meter. So here we have these rotors, and as the fluid flows in, it rotates these, and these just mechanically move the dials here. These are, a lot of times now there are smart meters and there's remote readings, but it used to be that an employee of the power company would come by every so often and would read off of here, and that's what you would determine your bill, or that's how your utility bill would be determined. And dads would be standing outside getting upset every time they see these dials spinning, yelling at you to turn off what you should have turned off. Maybe those days are gone. I'm sure they're still yelling to turn the lights off. I know I do it. Kids. Anyways, I digress again. The last one, I believe this is the last one we're going to cover, is the acoustic flow meter. There are a bunch of different versions of this. Two of the more common ways of doing this. I think there is a third way, but these two are more common. But you measure flow by sensing the difference in the measured transit time between the pulses of ultrasound propagating into and against the direction of the flow. So there's this version here where it goes through, you have a reflector and it comes back. There's another version where you just have this one here and one down here. But depending on the velocity of the flow going through, you get different speeds for the sound going this way versus going this way. And one thing to point out is the fluid is flowing this way, and the sound is traveling so much faster that because the fluid is going this way, it's not going to just take the sound down the pipe, but it does result in a measurable difference that can be translated into the flow rate. And then so this one here would be non-intrusive, right? It's just on the outside of the pipe. There are inline types. And then this one over here shows the difference between the transit, which would be this type, and the Doppler type. So let's watch this video quickly.
In 1842, Austrian physicist and mathematician Christian Johann Doppler observed that the frequency of sound waves received by an observer are dependent on the motion of the source of the sound, or the motion of the observer in relation to the source of the sound. Think about how the sound of a car's horn changes pitch as it goes by. This phenomena is known as the Doppler effect. So what does this have to do with flow measurement? Well, the same principle is used in some ultrasonic flow meters. Here's how. A Doppler ultrasonic flow meter uses a transducer to emit an ultrasonic beam into the stream of fluid flowing through a pipe. In order for a Doppler flow meter to operate, there must be solid particles or air bubbles moving through the stream that will reflect the ultrasonic beam. The motion of particles shifts the frequency of the beam, which is received by a second transducer. The frequency shift is linearly proportional to the flow rate. But what if your application doesn't have any suspended particles or bubbles that can be used to get a Doppler reading? That's where a transit time ultrasonic flow meter comes into play. A transit time ultrasonic flow meter measures the difference in time from when an ultrasonic signal is transmitted from the first transducer until it crosses the pipe, bounces back, and is received by the second transducer. When flow is present, sound moves faster if traveling in the same direction as the flow, and slower if moving against it. A comparison is made of upstream and downstream measurements. If there's no flow, the travel time will be the same in both directions. Since the ultrasonic signal must traverse the pipe to be received by the sensor, the liquid cannot be comprised of a significant amount of solids or bubbles, or the high-frequency sound will be too weak to travel across the pipe. So there you have it. If you still have questions, feel free to give us a call or chat on omega.com. Thanks for
That's a more modern flow meter. Okay, another question for you. Which statement best describes the error induced by a high viscosity fluid in a variable area flow meter? Actually, I think we already covered this one, didn't we? I think I have this question twice in here. So A, that's the right answer. Now, this one, a student asked how this works at one point way back, and I think it was a good thing to incorporate into the lecture. I think it forms a good segue into what would normally be the last topic that we would cover. So we're in the whole online delivery thing likely slowed us up a little bit. We would normally cover control systems as the last part of this. We only have the lecture on Thursday, and I probably should cover the final then a little bit, but maybe we'll still get into it. But let me just describe this, and then I'll describe how it's a segue into control systems. This is a mass airflow sensor for an internal combustion engine. So lots of cars have this. There are other versions of it, but generally what happens is, or not generally, exactly what happens is you have the air flowing through here. And there are these three little wires. It's not the wires across here, but there are these three little coils. And a constant current is set through these. And so current is set through, there's going to be heat generated. If the air is moving more quickly, it's going to remove more of that heat. So they're going to cool down. And so you're going to get more flow. So if it cools down, you get more resistance and you get more flow through it. And then if instead it heats up, if the air is moving through there more slowly, then it's not going to be removing that heat. It's going to heat up and the resistance is going to increase, which is going to decrease that current. And then that by measuring that is fed to determine how much what the gas air mixture should be. This will open up the throttle to let more in or let more air in or restrict the airflow in. So it's acting as a control system as well. So that's the segue part into the control system. But before we get to that, if we do get to that, that'll be on Thursday, our last day of lecture. Before we do that, we should talk about pressure probes. So this here, we're more specifically fluid velocity measurement. We need to define or review a few things that you probably already know the definition of. The first one is static pressure. So we use P with a subscript S. This is the pressure on the surface. It remains independent of the orientation. This would be like the pressure, say if you blew up a balloon, it would be the pressure pressing on all different sides of it. The next one is dynamic pressure. This one, P with subscript V, this also might be called the velocity pressure. And this comes from fluid in motion coming to rest at a perpendicular surface. It's like the feeling of standing in the wind. It'd be that pressure that you feel from the wind blowing in your face. That kinetic energy is converted into surface pressure. And then total pressure, P with subscript T, is going to be the sum of these two. Here we have a pedostatic tube to measure the fluid velocity. So what we have here, we have the flow. We have one tube and a second tube. And these tubes, so the first one is going to, first let me say this a different way. The static pressure that's present in here is going to be everywhere in here, right? It's like I said, like the inside surface of a balloon. It's going to be pressing on all surfaces. In this case here, though, we're taking the velocity and we're redirecting that down. So this here is also going to be that dynamic pressure. So it's the total pressure since it's both of those. And then if we, at this point here, if we took the total pressure and we subtract the static pressure, we can just get the kinematic or the velocity pressure. So like this slide here says, it's common for measuring airspeed in airplanes and speed in boats. Oops. This way. Here we go. So use Bernoulli's equation, and we'll set v1 equal to 0, right? Because it takes that velocity, it brings it in, it brings it to 0. So at this point, that v1 is 0, but at v2, it's not. It's still moving past. So we set v1 to 0, and we rearrange this for v2, we get to this. And we have this c in here that is meant to account for any kind of losses from this tube out here in the flow. We'll talk about that. This usually doesn't have much of an effect. It's usually pretty small and negligible, but we'll talk about that in an upcoming slide. So in that case, you would just use c equal to 1, unless you're told otherwise. But this equation is what we got to from using Bernoulli's and changing v1 to 0. And then if we are measuring a gas, the z is usually negligible because the effects of gravity on that gas are going to be small. So we can usually simplify it down to this. And this would be the difference between that total pressure and the static pressure. It would be the difference between P1 and P2. So like I said, C accounts for obstruction of the flow by probe, can be determined by calibration, typically roughly 1. It usually doesn't have much of an effect. So this here is really the equation that we use most of the time. An example of that, or first I guess we'll show, this is just a pedostatic tube on an airplane. Here's the example. So if the gas flow rate in a pipe is being measured by a pedostatic tube, the gas flow rate is constant. What is the gas's density? So like that schematic before, a lot of the same things. Here we just have a U-tube manometer. Previously, it didn't really specify what the differential pressure transducer would be, and you could have multiple different things, but in this case, it's a U-tube manometer, so you have to go back to the pressure measurement knowledge you gained. You're given that velocity of the gas. So remember, we're given the rate, we want to know the density. The manometer fluid density, that's 1.3 grams per cubic centimeter, gram cc. So that's this density. We want to know this density. Like I said, the first thing we need to do is we need to go back and use our equation for the U-tube manometer to determine that change in pressure between P1 and P2. We know the density, we know the height change, that fluid column. So we can just use this equation. We put in the 1.3 grams per centimeter cubed. We convert the grams to kilograms. We convert the centimeters to meters. We put in our 9.81 meters per second squared for the gravity. And we have the 0.25 meters for the height. We do that, we get a pressure change between P1 and P2 of 3,185 pascals. That change in pressure is going to be the total pressure minus the static pressure. P1 minus P2. So we can put that into our equation. So we should also, we're after this density, so we need to rearrange, square the velocity, but flip these with each other. So we get this equation. We plug in the change in pressure we just calculated. We were told that was 3,185 pascals. So we convert the pascals to newtons per meter squared, and then the newtons to kilograms times meter per second squared. We were given the velocity of 550 kilometers per hour. We need to convert the kilometers to meters, and we need to convert the hours to seconds. If we do that, we end up getting 0.273 kilograms per meter cubed as our density of the fluid, the flowing fluid that we're measuring. That's it for this lecture. We'll have another one for you and some more information on the final. The lecture will be on Thursday. You might get more information on the final before then. See you soon.